So the recording is on. So welcome everyone to today's lesson. What we will be covering in today's workshop is going to be mostly neural network programming with TensorFlow. So this is one of the beginners workshops with machine learning meetup group. To introduce myself, my name is Ali Parandeh. I'm actually one of the founders of the group. It's been, I think, about 2 or 3 years, and we've been started running some workshops in Microsoft Reactor, and now we're actually part of the Azure community groups. So Microsoft supports us with like teaching AI and machine learning on the Azure platform. However, we are more like an agnostic, cloud agnostic community group. So we teach not just Azure, we also teach AWS and sometimes GCP and even IBM as well. So we've done like workshops with IBM Watson and things like that. I myself was a mechanical engineer, but I changed into data scientist and later on software engineer. I have my own team as well in a tech startup right now that we build computer vision products. Basically, I felt like maybe we should run this session today to get into TensorFlow and neural network programming, because these are actually really hard concepts to grasp just by reading the tutorials online or just the documentation, like if you just go to on TensorFlow website and you just get started guides, straight they jump into like really complicated concepts that it's very hard to follow. So I feel like maybe I should just bring everyone back up a bit without straight jumping into maths or anything like that, and go step by step and actually like see how a neural network gets trained in action. And you also learn some of the concepts around how you need to prepare your data, how TensorFlow works under the hood, and like when you say model.fit, what does exactly happen under the hood. So when you train a neural network, what does exactly happen under the hood. Since this is a big topic, I will be just covering some very, very key concepts. So in particular, just some very key deep learning concepts, such as, for example, what are tensors? What do we mean by saying neural network architectures and how neural networks work? So just these main concepts. And then we will go into looking at some demos of model training, tuning, and not necessarily deployment. I think I will cover deployment in another lesson just because it's another big topic. But we will be looking at some Jupyter notebooks, and I will actually show you some live code in PyCharm. So that's why I said download PyCharm so you can actually play around with it yourself as well. The other thing we will do is we will learn the process of loading and preparing data for training. In between, if you have any questions, feel free to just either post it in the chat or just speak over me if you have any questions, and I can answer them. Also, you can email me later on. And basically, we will learn how to evaluate models and any common pitfalls that you may have. And in between, we will experiment with different TensorFlow model architectures and evaluation metrics. Does that sound good? Yeah, perfect. All right, let's get started. If you're not on mute, put yourself on mute so there is no feedback loop. Otherwise, if you have any questions, just unmute yourself and just let me know. I think at the moment I don't see any chat, but once in a while I will stop and then we can go into, I will look at the chat to see if there are any questions for anyone who cannot speak through the microphone. So this workshop will be mostly focused on the first module within this TensorFlow modules fundamentals. And we will be covering a couple of concepts. The main thing is, I just wanted to show you this is because this is like a massive landscape of AI. So this is the AI landscape in just the whole like 2021, someone that actually put this together. So there is a lot of tools out there, all right? And there is a lot to learn. If you want to learn it, it is a lot to learn. Some of these are startups and some of them are just like tools like you can use for doing ML. And like if this could be literally a whole career to itself, just deep learning. However, I've been through some LinkedIn job postings if your intention is to get into AI, you're not in AI, or you want to build your own AI capability in your teams, these are the main skill set that people are looking for. Or you might be looking for yourself when you put a data science team together. So you could become a full stack AI engineer by obtaining a subset of these skills yourself, like doing online courses, I don't know, doing projects, attending hackathons. Or you can build a team around this by hiring people from different sub skill sets. So that includes people who know cloud computing and DevOps, people who know data science and data visualization, people who are good data engineers and they know, for example, data engineering and big data skills. Machine learning engineers who are good at maths and stats, and MLDL algorithms, data science and consulting skills, or general software engineering skills. So if you're building like really large applications, that's like something you may need. And in all between here, you also may need some soft skills and collaborating software engineering development. All right. So before I go forward, I just wanted to show you something I've been working on myself. So because there's a lot of different concepts to learn, I am building my own platform. So I'm actually coding this platform. It's called buildyourai.com. If anyone's interested, let me know if you want to try some of the content on the platform. So the whole idea behind it is that you would be able to learn not just data engineering skills, but front-end and back-end engineering as well. And you can actually build an end-to-end app. So that's the whole purpose of this platform that I'm building. And if anyone wants to just be in the focus group with me and help us with doing some of the concepts and like, testing out different features on the platform, yeah, let me know. I will be emailing you. And once we release those features, you can play around with them and be one of the alpha users of the product. So with this, it's instead of like learning, like not knowing exactly what you're learning, you are shown some kind of like skill map, and then you basically dig in a deep dive in each one, and you build your skill set, and then you can actually build an app end to end. That includes building the front end, building the back end, building all the data science parts, and doing some coding experiences on the cloud, as well as like making the whole thing work, and building an AI model, training it, deploying it on the cloud, and then using it in your back end and make the whole thing work basically back to back. And you've got like stack based like community in there, and you can use some study tools as well to help yourself with some of the information management and the skills management. So if you're interested in this, yeah, let me know, and I will be sharing more details with you after the workshop. So let's go forward. Basically, the thing with AI programming is that it's very different from traditional control logic programming. So when you do software engineering, you sit down, you write if-else statements, you have conditional statements, you may do a for loop, a while loop, so on. Like it's everything is very deterministic. But as soon as you go into problems related to machine learning, everything becomes more probabilistic. For example, if you're trying to detect anomalies in like your server logs, or I don't know, detect anomalies in transactions, or detect spam in emails, like these are like applications that comes into my mind. Normally, these are like really hard problems to like write a logic control program for. So that's why you need to use data and algorithms to build basically functions. We call them models, that you give them inputs and then they give you outputs that you want. That's it. So you give them data as inputs, and then that data gives you outputs. Like an example would be you train an AI model to classify different types of objects for you. One example would be if you build an app that classifies like different breeds of animals, or different breeds of different. A healthcare example would be you pass it brain scans, and then it tells you if someone has some kind of disease or not. They don't have it, because some of these might be actually difficult for even doctors to identify. So these are like things that you use data to do that, and then you use algorithms to train a function in a computer to then process that model, right? So one thing you need to notice is that with neural networks, it is possible to do that. So with traditional machine learning, you have to analyze your data and figure out like which columns of your data correlates with your output. It is still the same with deep learning, but with deep learning, you actually don't need to do that much because you just pass all your data in, and then the neural network figures out itself what are the patterns it needs to identify, and then uses those patterns to take the input data and then figure out the output for you. To make it more sense, let me talk about how your brain actually works. So your brain is made of lots of neurons, right? They have a nucleus, they have an axon, and then those axons and nucleus, they connect to other neurons, right? The way it works is that the signals in your brain, in your neurons, go through each neuron and to the next one. And these neurons act like filters. If the inputs to these neurons are above a certain threshold, they pass that signal to the next neuron. If it doesn't, think of them like junctions. Whenever a signal reaches a junction, if there is a lot of them, they will go to the next one. Otherwise, they get stopped at that junction. So given a potential energy above a certain threshold, that basically that neuron will not fire to the next one, or it will fire to the next one. And using this logic, mathematicians have and computer scientists have put together more like a very simplistic model of it to create a neural network where you give a bunch of inputs, and then based on that mathematics, it basically represents exactly the same behavior that your brain simulates when it's learning a new skill. So for example, when you learn to play piano, at the beginning, you're not very good at it, so your neurons is firing all over the place. But as soon as you get better and better, a certain pathways in your neural network in your brain keep becoming activated and activated and activated because of these like patterns of activation potentials happening again and again and again in a repeated manner. That's like that's for example when you practice piano and you become really good at it. And that's how you actually learn, like those neural pathways that keep becoming activated and signals keep going through it. Those pathways become really, really like strong and really thicken using some kind of like liquid loop that goes around them and the activations. And that's how you learn that skill. And in computer science, this is simulated using this neural network logic that you see on the right-hand side. So you take the bunch of inputs, you multiply them by their weights, and you do this layer by layer. You add them all up, and then you put some kind of activation function at the end to get the output, and then you construct your neural network, and that mathematically simulates exactly how your brain learns. So this way, we can teach computers through data, through input, to learn to identify patterns from the data to the output you're looking for. That's the whole concept behind deep learning. Is that instead of like sitting down and like doing machine learning by hand and like using clever statistical mathematical functions or whatever to get what you want, you actually just feed the data to this mathematical formula or algorithm, and then that mathematical formula just numerically figures out a function that maps the input to the output. So if you look at one neuron, for example, this is what it could look like. You have a bunch of inputs, x1, x2 to xn. It goes to this neuron, and then that neuron applies a function on it, and then you have an output that is called y. And if you connect multiple neurons together in a brain, which is like a neural network in your own brain, this is what a simplistic representation of that looks like in your brain. You have a bunch of inputs, they're connected to a bunch of output nodes. Those output nodes are then inputs to the next layer and next layer and next layer until the end. So you go all the way to the end this way. And all it's happening is that these inputs get multiplied by their weights, and then they all get added up. You might also have add biases. And then at the end, you apply some kind of activation function to give more degrees of freedom to your neural network to learn. So that's the whole purpose of the activation function. I will go into it more in detail, what the purpose of that activation function is. and then you get the output from each node. And then you do this for every node in the network. And some of these networks are large. Like the simplest network we will work with today is like, the dataset we will work with is MNIST fashion. It's like 32 by 32 pixel inputs we will give it. It's like stat is like nothing. It's really small. Normal images are about 720 pixel by like 1600 pixel or something like that. That's a lot of like input data to give to a neural. You need a massive neural network to process that. But these are like called multi-layer receptrons that make them easier to understand for beginners to understand how they work, and then we go from there to the next stage, right? So that's how it works. Basically, you have a bunch of inputs. You multiply them by one bunch of weights. You add them all up, and then you add some bias as well. You apply an activation function, and then you get the output. And then you do this for every node. So when you're working with TensorFlow, and TensorFlow is actually like taking the data in a process and training a model, it's doing all of these calculations under the hood, mathematically speaking, until it gets the output from the output node. So normally the inputs are a vector of numbers, and then the output is a vector of number. And I will go into more detail what these numbers exactly mean. But that's like, in short, how you pass data through a neural network. It just becomes converted to numbers, and then those numbers just go through the network, getting multiplied by other numbers and getting added up, and then basically just get through that number from one layer to the next layer until you get another number at the end. But in this process, certain pathways keep becoming more active, I would say. Like the numbers, the way it works is that those numbers in those certain pathways become really, really high compared to the rest. And that's like the simulation of the neural pathways in your brain that becomes activated much more until you learn that skill. It's the same thing with this in a mathematical form. Okay. So before I go forward, does anyone have any questions regarding like how neural networks might be working? Yeah. Yeah. So this is an example of how a neural network work for images. So you're asking, like, for example, how does different layers learn to identify like whether they're looking at a cat or a dog, right? So, or a truck, right? So here's an example of how things work. Let me just add people in. So if you look at this, this is actually from the Convolutional Neural Networks course for Stanford University. Each one of these columns represent a layer in the neural network, right? So when you pass in the image in, every layer sees different patterns, and then those patterns get passed down from one layer to the rest. And think of each layer as a filter that you apply on that image. You know, like Instagram, when you apply a filter before you post your picture, right? Think of it as the same. Like, think of these as like bunch of Instagram filters that you apply one layer after the next, and then by the time you reach the last layer, there are certain patterns in that last image that makes it really easy for the computer to understand if it's looking at a cat or a truck or a dog or a ship. So the computers, like this, I will tell you exactly what this image is under the hood in the computer. this image is not exactly, it's easy for you to see this because we are humans, like we see that picture, we can see it's a car, right? Computers don't see those pictures like that. They see it as bunch of numbers, zeros, and like zeros to 255. They see a grid of numbers, right? If you look at a grid of numbers, like take a piece of paper, like make a massive matrix of numbers in it, like 500 by 500 matrix of numbers. Each number could be between 0 and 255. You will have no idea what you're looking at because it doesn't look, it doesn't look like anything at all. It's just a bunch of numbers. That's what computers see under the hood. So they need to do all these like different calculations and different filtering. We call it convolutions to understand, to basically to identify the patterns in the image in order to classify them. Here we see the picture, we see the outputs, not the weights and the biases, right? So these weights and biases, so this WI for the first node and then WI for the second node, these are called the weights. And then biases are just basically, I think the best way to do it is if I show you actually in Figma. Let me open my Figma and then show you a piece of drawing in there. So if I open a FigJam, and this is just a drawing tool, so I could actually show you what's happening. So if you imagine we have an X and Y, like this is our Y-axis, this is our X-axis, and we have a line, right? The way you define that line is AX plus B equals Y. Right, that's the function for that line. If you increase the B, the line goes up. If you increase the bias, the line goes up, and then if you decrease the bias, the line goes down. If you increase A, the line starts going this way, and if you decrease it, it goes that way. If you decrease A, like go towards negative, it becomes this, and if you increase A, it becomes like that. Right, that's how you define the function for this line. And that's just a simple line. So each one of these nodes, where is it? Where is my, let's go here. Each one of these calculations, x1 multiply w plus b, that's just one line. That's just like the definition for that one line. And then you add up all of that together. And when you apply the activation function on top, it will basically add a bit of nonlinearity to just makes a neural network more capable of expressing more, identifying more patterns. The easiest way for me to describe a neural network is like, think of this neural network, whether it's a non-deep network or a deep neural network, where you have like every node connected to every other node in like different layers. Think of these neural networks as like a massive black box, and then like, like a safe. With the safe in a bank, it's got, and then think of this safe in a bank with a black box. It has lots of knobs and dials on it, and when you train a neural network, you're literally just like playing around with these knobs and dials so that like the input data gets mapped to the output data. So if the input data is a vector of numbers that comes from that image, this image, and that image gets mapped to the classes, like if you have like 4 classes or 10 classes or 10 categories of images, it gets mapped to those 10 categories of images through these like connections. And each one of these nodes allow each one of those weights and biases are the knobs and dials that you can play around with to make this mapping work. So since humans can't do this, like you can't sit down and do this by your hand. I mean, you can if you want to. You're gonna have a hard time because it's just basically differential equations left and right. We normally do it using numerical computational approaches, which basically means you compute an image going through the network. You take that image and then you compare it against the output, and then you go back and change the knobs and dials. You do it again, you go back, change the knobs and dials. You keep doing it until your loss function goes to 0, until like you don't have any more errors anymore. So that's like how in practice neural networks work. There is this YouTube video that is really good. I'll post this link for you so you can watch it later. I would definitely recommend watching that. If it's really good. And that guy will exactly like give you lots of visuals on how neural networks work, under the, like, mathematically speaking. But in reality, this is what it looks like. It's just when you visualize every convolution, every layer one by one, this is what you see under the hood. But think of each of these images as a matrix of numbers. When you visualize them, they look like this. Like, to a human eye, they don't mean anything, but to the computer, the computer sees patterns that they can use mathematically to map that image to a class. And in computer vision, this is a simple problem it's still a hard problem, but like this is the simplest computer vision neural network problem. Harder ones are like when you have to like identify like where the car is in the image, or where the dog is in the image, and different dogs have like different lighting conditions. Different images have different lighting conditions. The object might be in different angles. It might be half of the object might be hidden, like obscured. They might be moving and have some kind of halo around them. So there are all of these variables that make it hard to be for different types of computer vision problems. And we even have like segmentation problems where you actually have to like, you shouldn't, instead of like just giving a label of like this is a cat or a dog, and not just identifying where the cat or a dog is in an image, you have to actually draw the boundaries of the dog. Those are called segmentation computer vision problems, and they're the most difficult one to do, because there are so many like variables you need to play with for your neural network to learn, to be able to like draw exactly the bounding boxes, not even a bounding box, but like the boundaries of the dog in the image. So what I mean by segmentation is this. This is a segmentation machine learning problem, computer vision problem. So this is done by a neural network, but like there's like the data, like the neural network is basically spitting out exactly the coordinates of every pixel of this guy, so that you can draw this red halo on him. Same thing with vegetation, same thing with the cars and with the road and the signs. Like these are like a lot of data has gone through this neural network to learn this. And in automotive, this is how they're using, how they are training up autonomous vehicles to basically drive automatically in streets. So Ash is having a question. Hi. Yep. 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 Good to see a fellow mechanical. Yep. Yeah, you need this. I would suggest you get this book. So this is quite a thick book, but your problem is a natural language text processing problem. So documents, they are text, and the way you work with text is that you convert them to an array of numbers using natural language processing tools. So at the end of the day, any natural language text problems, they are actually there is a process called bagging. You basically create a dictionary of, like, for example, words, or you create a list of words, and then you convert those words into like numbers, like an array of numbers, right? And then you use that. Yeah, and then when you have an array of numbers, it becomes a maths problem. Right, that's how you do it. But get that book. It's called Natural Language Processing in Action by Hobson Lane. I think if you search it on Amazon, it will come up, and it will teach you everything you need to know about NLP. Yeah. So, but the thing is, learn this computer vision problem right now, because once you learn how neural networks work, natural language processing or computer vision or any other data set, you will learn how you can train any data set. So, like, the purpose of this workshop is to teach you how you can train any data set. So we will, as long as you learn how you can wrangle the data to the format that is required for training a neural network, that's all you need to know. You don't need to know like what the initial data set could be. It could be a video, it could be a binary data, it could be structured data. You can get that data from database, IoT sensors, anything. If you learn how neural networks work and how you put stuff in it and you get stuff out and you train it up and how you can evaluate it, you can basically build your own AI models. But no, you're welcome. So, Stefan, like, to answer your question, yeah, I'm planning to make this into a series, because I feel like this is actually really useful topic for most people, and the what's it called, the resources out there, it's good. They're really good resources out there, but still very difficult to follow, some of them. So I wanted to just like make these into some kind of series where we go from beginning all the way to the end, doing different topics each one. So I'm building the content at the moment. I would suggest until then go through these TensorFlow modules from Microsoft, but basically I'm building my own content, and I will be putting up them on my own platform, which is that buildyourai.com. But if you're interested, I can send you. I can put you on waiting list for that once it gets released. If anyone else wants to be on the waiting list, let me know, and you could get access to the content and play around with it. And also, like, any recordings from these workshops and then all the materials like the slides and the code, I will put it up on the platform as well. So once you log in, you have everything there. You can go through it at your own pace. So I'm not sure if I can spell it correctly, but would you check? I think he's asking how close is artificial model to the real work of human brain. It's not close, so that might be surprising to you, but there's mathematical like operations that we do to map neural networks, to basically train up neural networks that are artificial. They are so simplified compared to human brain. Like, human brain has like much more complicated than like a simple neural network. That, like, even like the most complicated neural network that you can see in use in production is still simple compared to a human brain. And I'm sure like neuroscientists still don't understand half of human brain and how it works. For example, here's one thing I would like to tell you. There is a book called Mastery by Robert Greene that I would suggest everyone to read to learn more about how human brain works and how people actually become masters in their field. One of the things it says is that your brain like physically changes its structure. So, like, if you learn a skill and become a master, like in playing piano, your brain physically changes its structure. So it's not just that your neural networks become much more active. It basically your prefrontal cortex processes that new information and then builds a skill, and then it basically stores that skill as like a file down there in your bottom of your brain, and then it becomes free again. It's like a RAM that becomes free, and then you can use that to do something else. So that's how you get some of these like piano masters, like they can play piano at the same time, like think about what they should have for dinner, you know, like or like they could play piano with one hand without even thinking, because like that skill is like so automatic, and that brain has like managed to find a way to like make that skill pathway in neural network much more like compressed and more efficient. And we're still not there yet with like mathematical operations and artificial intelligence in computer science. Like there are like tools out there that are called neural network pruning or node fusion. Like you might have heard of these concepts where you take a massive neural network and you just basically take pieces of it and you fuse the nodes together, so that you summarize the same neural network but with a smaller neural network, or you prune bits of a network that are not useful so that your size of your neural network reduces. But still, with this, it's still hard to simulate exactly how the brain could work. And then Rabea says, what are the weights? I mean, when you said input is multiplied by the weights. So Rabea, weights are basically knobs and dials on the black box. So if your neural network is a black box, you play with the weights and biases to map the input to the output. So when you take the data in and then you get an output, you look at the output versus the output you expected. And then if there is an error, you play with these knobs and dials to then match the input to the output exactly the way you want it. And that process is called training a neural network. So you use these weights and you play with the weights and biases. So when you say model.fit on TensorFlow, what TensorFlow does is that it uses an optimizer function to bring these weights and biases up and down based on what it calculates to be the right value, the learning rate, and then it then passes the next batch of data through the network to see how it performed, and it keeps repeating that in each epoch, or in each training cycle. We call that epoch. But we will get some actually action, and you can see that in Python, and when we get to that stage. So basically what we will be looking at are a couple of deep learning frameworks. There are quite a lot of them out there. The most important ones are TensorFlow and PyTorch. So Keras is now actually part of TensorFlow. I think previously, before, TensorFlow 1 didn't have Keras in it, but now TensorFlow 2 does. And it's actually a big part of TensorFlow 2 is how it works is using Keras, which actually make it very declarative. You just tell TensorFlow, I want a neural network that has this many nodes in it, that many layers. I want this layer to be like this, that layer to be like that. So it's very declarative, and it's very easy to work with. PyTorch is another deep learning framework, and most of these deep learning frameworks, if you look at their GitHub repos, they're mostly written in C++. Sorry, they're mostly written in Python and C++. So the reason they're really fast is because C++ is a language that uses pointers. So you can, when you have access to pointers in a language, that means you can manipulate memory in a computer. So, and you can like do some really advanced stuff. So because they have access to pointers using C++ and they're also written in Python, they allow these frameworks allow you to run really efficient mathematical operations, and even like, you know, move the computations on GPUs, which are graphical processing units. So they most of the calculations are done in matrices, so that's why you need to learn linear algebra. And on normal CPUs, these computations are done synchronously, so you multiply one thing, then you multiply the next and next and next. When you move stuff onto a GPU, everything can be done in parallel. Like you can multiply like n-dimensional cubes of numbers or tensors, and like at the same time, and they're really fast. That's why like training neural networks on GPUs are really fast, because you can make really massive calculations on really massive arrays of numbers that are multidimensional, using those deep learning frameworks. And the way you do it is actually quite simple as well. This is the example that TensorFlow gives you. It's literally 15 lines of code. All you do is import TensorFlow, use the tf.keras datasets.mnist to basically download the mnist dataset and put it into this variable. And then when you do .load data, it literally just like gives you the dataset for mnist, which is that mnist is 60,000 images of handwritten digits. So it gives you 60,000 images and 60,000 labels. So that becomes your X train. 60,000 labels becomes your Y train. These are vectors. So these are lists of images and lists of labels. And then X test is list of test images, about 10,000 of them. And Y test is a list of labels for testing, basically for these test images that are X. So anywhere you see X, they are images. Anywhere you see Y, they are labels. And you divide them by 255 so that your images are normalized. And what I mean by normalized is images are an array of numbers, right? So if you think of an image, just think of a matrix of numbers. So that's an image, for example. I mean, my handwriting is not very good, but and then the numbers in each cell are between 0 and 255. 0 representing black and 255 representing white. So in a grayscale image, for example. And when you normalize it, you convert the 0 to 55 to 0 to 1 by just dividing everything by 255. And the reason you do that, so if you think of the distribution plot of the pixels, so if the y-axis is the count of pixels, and then the x-axis is range of pixel values. So this is 0, and then this is, let's say, 255, and then let's say you have a distribution that looks like this, right? When you normalize it, the only thing that happens is that instead of 255, you have a 0. You have 0 to 1. That's it. Like, your distribution doesn't change. It's just that your values become between 0 and 1 when you count how many of these you have in this array of numbers. And the reason you do this is because your network will learn much better if your numbers are normalized between 0 and 1 instead of 0 and 255. Mathematically speaking, otherwise you will overshoot all over the place when you try to reach a solution in a numerical problem. So you divide here by 255, and then you build your model using this sequential layering framework. So you say tf_keras.layers flatten. So you put the image and flatten it. So you convert a 28 by 28 image into an array of numbers. So that's how much is a 28 multiplied by 28? It's 784. So an array of a list of 784 numbers. That's what the flatten does. You pass it through a dense layer of 128. You use dropout to reduce the overfitting. So you make sure that your model doesn't overfit to the data, and then you pass it through another dense layer, and then you apply some activation functions to make your model learn a bit better. I will go into more of these, what they mean, but that's how you define your model, and then you compile it. So in compilation, basically you tell it what algorithm you're going to use to optimize the knobs and dials, the weights and biases, and what function you're going to use, what algorithm you're going to use to check how good your model is doing. So how you can calculate your loss. So loss here is when you compare the output of your model versus the actual output. So the difference is called the loss. And you could either just minus it, or you could use something called the sparse categorical cross entropy. I will go into detail as well what all of these are and what metrics you're going to use. So accuracy is basically how many of your test samples did you actually predict correctly, and that's called the accuracy. And when you do model.fit, that's where the actual training process happens. Epochs is the number of training cycles. So If you have 60,000 images, you will basically go through all that 60,000 images 5 times to train the model. You pass those in 5 times to train the model in batches. And then at the end, you evaluate your model with an evaluate.evaluate function that you pass the test images and then the test labels. And then that's how you can actually get the accuracy for your model. And that's it. That's the whole code for training your model. Obviously, if you replace MNIST with your own data set, so you pass in an array of numbers and those numbers have labels, you can actually do this for any data set. Right? But like, this kind of like modeling is not always like using the sequential modeling is not always right, because sometimes it's not appropriate for all kinds of data sets. So you might have multiple inputs, outputs. Your layers might have input, outputs, and things like that. So there is just like some caveats you need to worry about. But this architecture you see here is very similar to this architecture, basically. So that's just, you have a bunch of input nodes, and then you have some dense layers, and then a bunch of output nodes. However, there are way more architectures out there. So that's why deep learning becomes more of a art as well, rather than just science. So knowing which one of these architectures you need to use for your data set is actually a whole body of knowledge to learn. So for example, for natural language processing, LSTMs and RNNs, recurrent neural networks, so these are like nodes that have like relations to themselves. They have like connections to themselves. They are very good at they are called long short-term memory, because they are basically good at retaining information about sequences of numbers or sequences of patterns. Other networks are more useful at like identifying patterns in an image. It's kind of, for example, convolutional neural networks. So depending on like different applications, you may have to use a different architecture, basically. And there's a whole body of knowledge around which one you need to use based on what application you're trying to build, what AI model you're trying to build. And that's why this is part of an R&D problem. So whenever you're building an AI model and it's not performing well, either you go back and improve your data, or you go back and you play around with hyperparameters, or you go back and play around with the architecture. And this is just like a R&D process. Like, you have no idea which one is going to work. Which ones, you probably know some of them work better with some data sets, some of them work better with other data sets, but at the end of the day, like, you have to decide between them, or play around with different architectures until you get the one that you want. But defining your neural network architecture using these different layers, each layer has a purpose. So dense layers are very good at like giving your neural network enough knobs and dials to map your input data to output data. Flattening layers are good when you want to like take an array of numbers and put it into a vector. And dropout layers are useful for preventing your neural network from overfitting to your data. So what dropouts do is like they actually they stop some of the neurons from firing. So remember these neurons here? They actually stop some of the pathways of neurons from firing, even though they receive a lot of input. So they basically artificially prevent some neuron pathways from firing, from letting signals pass through those pathways to prevent overfitting. That's what the dropout does. So in a fully connected neural network, which is this, imagine some of these connections don't work at all when you put a dropout layer. That's what it does. It randomly disables some of the connections to prevent those connections from overpowering the other connections. So when some connections start overpowering other connections, your neural network starts to overfit, which is a process of like, imagine a kid that you imagine you're a parent and you have a kid. Your model is your kid, and you're trying to teach your kid to prepare for an exam, and you start giving them some exam questions, and then they start learning those exam questions. They do really well, but then when they go sit in an exam, the questions are completely different. But what they've done is they have memorized the answers to the questions that you've given them, but in the actual real exam they have no clue how to answer the exam questions. That's called an overfitting. So the training data you've provided the model has overfitted to that data, but the real data it doesn't have no clue how to deal with the real data when you want it to. So it's not generalized enough. That is when you start adding dropout layers in your architecture. But I suggest that's enough of like concepts. How do you think we should maybe jump into some code to actually get some real action in? But before I do that, there is actually some things I wanted to mention as well. You can actually define your own custom architectures using this class definition as well. So I'm not sure how familiar you are with Python programming, but in Python, if you know object-oriented programming, this should look familiar, this type of writing classes. So you basically inherit from the model class in Keras. You define your initiation function, and then you define a call. You override the call function, and you basically define the architecture this way. So this gives you more power in terms of defining your model architecture. But I'm not going to go into detail because this is a bit more for more advanced users. And one other thing to know is that when you are working with TensorFlow, you're going to be working with something called tensors. And tensors are just basically, think of them as specialized data structures for neural network programming. So when you have a number and you put that number in a list, you have a vector. So when you have a list of numbers in Python, that's called a vector. You can even use NumPy array to convert them into a NumPy array. And NumPy allows you to create like matrices as well. But what tensors do is you can convert all of these into a tensor, and tensor is like a box that are very efficient at mathematical operations, and they are a data structure that you can pass them around between CPU and GPU. So remember, I said in GPU you can apply mathematics at a much bigger scale. So if you imagine of your tensors as a bunch of boxes, you have a 1D tensor, which is a list of numbers, a 2D tensor that looks like a paper of numbers, and then 3D tensor is a cube of numbers. A 4D tensor is a list of a cube of numbers. So imagine you cube bunch of numbers together and then you put them in a list. 5D tensor is basically you create like a warehouse of you create like basically a page of cubes that have numbers in it, and then a 6D tensor is basically a cube of cubes of numbers. And then when you put them on GPUs, you can literally multiply these cubes of numbers together, like when you multiply two matrices of numbers together, like a dot product. On a GPU, you can actually multiply all of these cubes of numbers together using tensors in like split of a second in parallel. And that's why they're so powerful. That's why neural network programming and neural network training on GPUs are so much faster than CPUs, because you can do all these massively parallel operations of calculations of numbers on GPUs, just like that. So training a neural network is literally just calculations of like multiplying numbers by each other, adding them all up, and then comparing the last number with the number that you expect. And then if it's different, you go back and you change the weights and biases. You do this operation again, and then you do this back and forth until the weights and the knobs and dials on your neural network are all fine-tuned to the data that you have. And you need to perform these like mathematical operations at this scale to be able to achieve this for like very complex data sets, such as segmentation of images, or if your data set has like lots of dimensions in it. So think of a spreadsheet that has like 50,000 columns. Sorry, not 50,000, but like 20 or 30 columns, and like a lot of them have like relationships and correlations with each other. Or like images where there could be any sort of pattern in the image that would allow the computer to see if it's looking at a cat or a dog or whatever. And obviously, once you go past the GPU, you get to a TPU, which is a tensor processing unit. So these are specialized processing units developed by Google for just neural network and deep learning. And you can just see like this orange dot up here, that's how fast it is. So the GPUs, like the best GPU, like back in the day, was GTX 1080i, like the Titan, was like 15 G flops, but like this one is like 40 T flops in terms of like how powerful this is in terms of in parallel computing the calculating all of this other stuff. So very, very impressive where we've come so far. And lastly, what I wanted to mention is computers under the hood see images as an array of numbers. So when you look at a colorful image like this one, under the hood, computers see the images as array of numbers, especially free array of numbers, like topped on top of each other. One array represents how red each pixel is. One array represents how green each pixel is, and then the other array represents how blue each pixel is. And your screen renders the colors on it based on the combination of these red, green, and blue. So if the number is around 0, that means that color is like literally near nothing, like the opacity of the number is near nothing. If it's 255, that means it's like you have a lot of greens. So if you have 0 in all of them, you get a black, and you have 255 in all of them, you get a white. And anything in between, you can get a combination of different colors using this. So that's how you can actually define a picture in a RGB color scale. So when you pass color images to neural networks, you have to flatten this 3x3 cube of numbers into a list of numbers and then pass that in. So you need a lot of, so like for example, for this, what's the size of this, what's the shape of these matrices? They're like 4x4, 16 multiply 3. So 4 by 4 by 3. Why do I have a dollar sign? That's 48 numbers in there, and that's just a 4x4 pixel. A normal image is about 700 by 700 pixels. Like, let's say 1280p by 900 by 3 color channels. How many pixels is that? That's 11,520 pixels. That's how many input nodes you need to have in your neural network to just pass that image in. And that is a lot of input nodes. So normally what you do is you either crop that image to a smaller image, like let's say 400 by 680, or you resize it by making it like smaller, divide everything by 2 into like a much more manageable image. So 340 by 200 to get like a smaller input node. So instead of having like a 18, I don't know, like what was the previously, like it was about like 200,000. It was I think about like 2 million or something like that, 20 million. Now you have about 204,000. And sometimes you even get rid of the colors as well. You grayscale it. So you get rid of the color channels and you have one color channel. And you pass that color channel in 68,000 numbers you pass in. Any questions? I mean, that was a lot to cover, but I'll just take a break before we actually go and play around with some code. Yeah. Okay, so I would suggest, so I'm a product manager myself, but I moved from tech into product management. I would suggest to understand how things work, um, to understand like how all of this work with the neural networks. It's too difficult for you right now to get into programming with TensorFlow because you will not understand what's happening under the hood. I suggest learning a bit of Python, like do like Udacity's Intro to Python course, so you understand how Python works a bit, and then look into how TensorFlow works, because otherwise, like things will just move across your head. Like you understand the concepts, but you don't understand how the code works when you look at the code, and you don't understand like you may be able to understand like the limitations and like what is possible with ANNs, but basically, in order to be able to know how what your developers can do with ANNs, I suggest just do a bit of like a basic Python programming course. It's very easy to learn Python, and just like how different data structures there are in it. And then I will now show you how, actually, like in the second part of this module, in this workshop, I will show you how the code runs, like what you see inside the code. And then you might be able to get some clues of like how it works under the hood, but knowing Python would help you. Right? Yeah, perfect. But the thing is, I will do a course on NLP. Like I will do another workshop, but this time focus on NLP. So just keep a lookout on the meetup group and emails. No worries. Stefan, did you have a question? Yeah. 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 So as part of training, you can pass in, so you can split your data set into two groups, a test set or a training set, or you can split it into three groups. And basically, when you split it into three groups, it allows you to basically look at how the training is happening as you train it. So in here, we're only passing in the training data to the fit function, but we can split it into three sets called validation set, training set, and test set. Test set is just a piece of data that we're not going to show the model at all. We're just going to put it aside so that Those are the exam questions that we're gonna ask from the kit, right? The validation set are more like homework questions. So training set are like exercise questions. You know, when you go to a class and I give you some exercises, validation set is homework. I will give you homework exercises to do, and then I will check you against those. I will mark you against those homeworks to see how you're doing. But you're not like it's not as effective. Like it's not like you will not get much penalized on it. It just helps me to understand how good you're learning as you're learning. But the test set is the exam questions that you will get the actual marks on, if you look at it as a university analogy. So when you don't pass in the validation set, it's as if you're teaching a kid some skill sets, like I'm teaching someone piano, but I'm not giving them any homework. So I don't have no idea how good they're learning, because I'm not like testing them on their learning as they're learning stuff. So that's the purpose of the validation set, is to just know as your model is learning, so you can see how the model is learning as it's learning it. Yes, it's only the train data that's used for updating the weights. No worries. So normally you use validation set to understand if your model is overfitting or not. So normally with your models, I think in here, let me see if I can find, I think it was in this one. Let me see if I can find that chart that was very useful to show you. This one. You get a chart like this. So this chart shows you the loss value as you train your model. So the more the loss drops, the better. The green line is your training loss. The orange line, the orange line is your training loss. The blue line is your validation loss, right? So normally what happens in overfitting is your training loss keeps dropping all the way nearly to zero, but your validation loss starts going up. That's when you have overfitting. That basically means that your model is really like memorizing all the exam questions, but it's not doing really well on like the homework. It's not doing really well with the actual, they might not be doing much well anymore with the actual data that you may pass it in. So that's when you start using validation set to just so you can stop the training. You don't overtrain a model. So you can keep some kind of, it's like some kind of monitoring. You monitor the model training with it. And then the test set is as if you do unit tests. It's actually when you test the model before you deploy it into production. So here's the same thing with accuracy. So the accuracy of the training is going up. The other one is going up as well. If I go to the next module, I think it might have some other examples that I can show you of overfitting. No, it doesn't have it here. No, I don't have it here. But what we could do is we could actually get started looking at some of the code and how it actually works under the hood before we get completely into it. Here's another example of one of these accuracy and validations. So I think the blue line is the accuracy of the training, and then the orange line is the accuracy of the validation set. So they're both going up. If one of them starts dropping, it's when you want to stop the training. Otherwise, you overfit. Right. So I think the blue line is your training. So it shows that your training accuracy, like your model accuracy, is going really up, but your training accuracy is like flattening. It's like dropping or flattening. That's when you want to stop your training, because then your model is overfitting. And by overfitting, I mean this. This is what happens when you overfit. So if you have two data sets and you're trying to separate them with a line or with like some kind of like generalized line, so you have some kind of function that if you give it a data point you fall on one side and then you give it another data point, you fall on the other side. This is like the proper fitting. But when you overfit is like when you have like really complicated like red lines, you're drawing around your data to classify your data set. And that is called an overfitting. Normally happens when you have lots of knobs and dials, like you've added too many knobs and dials to your model, or you have given it too much of the same data. That's what happens when you overfit. And underfit is when you're just using a really, really simple model to classify a really complex data. Like for example, on the left-hand side, you have these green crosses and circles, and you're just using a straight line to classify them. All right. So let's jump into code. This is what I'm going to do is I'm just going to go to my desktop. All right. And then basically in here, I'm going to make a folder called workshop. So I'm going to go in there and I'm going to open my PyCharm in that folder. All right, so I'm in the workshops now. PyCharm created me this file. We don't need it. What I want you to do is open the terminal. If you're on Windows, have you worked with Git or Git Bash on Windows? If not, if you're on Windows, install Git. Git is this. So Git is a version control system, and install Git Bash, which is like a terminal for Windows, Git for Windows, sorry, this one. Install this. It gives you a terminal similar to the terminal I have on Mac. And then you can literally write the same commands that I do. But I will provide this recording so you can, if you fall behind, don't worry about like following along with me. Just basically watch as I do stuff so you can learn and practice in your own time. But basically what I'm going to do is I'm going to go to the GitHub repo that I gave you. I'm going to clone the repo in my folder. So I'm going to do git clone. I'm going to clone the repo. If I refresh my PyCharm, you would see the clone, you would see the repo here. Right. So what I'm going to do is I'm going to open this repo, open this intro to Tensorflow project. And now we're inside the repo, right? So this is basically the project, and it's got a README and everything. And I'm going to set up my local development environment so that we can actually run this code. So I have two scripts here, and I have a requirements file. We're going to use the requirements file to create the environment, right? And then we're going to use the we're going to just basically use, once that environment is set up, we can then run these two pieces of code. One is PyTorch, one is TensorFlow. And they're exactly is the same, they do the same thing, but they're written with two different frameworks so you can see how they work. All right. PyTorch is a deep learning framework by Facebook. TensorFlow is a deep learning framework by Google. All right. And in both of these testers, in both of these scripts, what we're doing is we're training on MNIST fashion. So if you don't know what MNIST fashion is a data set for that looks like MNIST, but it's basically for classifying that's not very helpful, is it? It's basically for classifying images of fashion items in a very low resolution images. So these images are like 32 by 32 pixels, and they all have labels. between 0 and 9, I think, or 0 and 8. So each number represents a class. One is pullover, one is a trouser, one is a bag, and I think there's about 60,000 images. So this is a bit more complicated problem compared to the normal MNest, which is the hand-drawn digits. And basically what I've done here is just I've defined some variables. I'm loading the dataset, fashion MNest is called, into train images, train labels, test images, test labels. I'm normalizing them. Then I'm instantiating my neural network. I build it, compile it, and then print the summary, and then I train it, and then I just basically do print loss and accuracy. That's it. Right? But in order to run this code, we need to have installed TensorFlow and PyTorch. Okay? Do you know how to set up your own local environments with your local Python development environments? The easiest way to do that with PyCharm is you see down here at the bottom right, it says no interpreter. Click on it and click on add an interpreter. And basically just click OK. And that's it. Now you have an environment. This is the environment. It's got the libraries you're going to install and basically bin folder. And what I'm going to do is down here just basically say pip install. Let me just look at the help of it. If you want to pip install using a file, we pass it the R flag. So pip install -r requirements.txt. I'll just basically paste that for you in the chat so you can follow along. And when you do this, it will basically install this environment for you. So let me just basically close this terminal and open it again. So you know that your terminal is active when you see this env name, which is the name of this folder that's created here. That's your environment folder. So whatever packages we're going to install is going to go inside this environment. You can either do it this way, or what I like to do as well, which is normally a better way, you see this error, you see this warning sign that says up here package requirements missing, and there is an install requirements get ignore requirements. Just click on install requirements and let PyCharm install all of this for you from the requirements file. Done. All we have to do now is wait for the installation to complete. It's as easy as that. That's why I said download PyCharm. It just makes setting up environments so easy. So that's the command that is running under the hood. Pip install all requirements. So while it's doing it, does anyone have any questions? PyCharm. Yeah, that's fine. As long as you can run this code in your environment, that's fine. You don't need to install PyCharm. Yeah, what you need to make sure is that you can import those packages, TensorFlow and PyTorch. As long as you can import them, then you're good. You don't need to use this software. The reason I love PyCharm is because it gives me debugging tools. So I could teach you this stuff in Jupyter Notebooks, but I decided to use PyCharm is because I can stop the execution of the code anywhere in here, and then I can show you what's inside each variable. Okay. So you click down here, add interpreter, right? And then you press OK. That's it. Like it is in virtual env environment, new environment. You can name it anything you want. I named it TPYF, like TensorFlow PyTorch /env, and then press OK. And it creates the environment folder for you. You see it here. And close the terminal and open it again so you can see that your terminal is active on this environment. And then if you haven't installed the packages, you would see an error, and then basically you could see an error, and then you could basically use that to there will be an install requirements. You can click on it and it will sort it for you. It will install the packages for you. I think it still hasn't seen TensorFlow, but if you look in here, if you can see TensorFlow, you're all good to go. Let me just check if I have TensorFlow. Yeah, I have TensorFlow installed, so all is good. And then if you want to run the script, you see this play button here, down here. You click on it and you say run TensorFlow demo. Looks like it hasn't installed TensorFlow. Let me just check if I have TensorFlow in here. Yeah, it has TensorFlow. What I'm going to do is I'm just going to search TensorFlow and install it just in case. You can also install packages from the Python packages tab. Search the package and press install. For some reason it didn't install TensorFlow. So now it's installing it. So while it's doing that, there you go, it's now installed it. Wait for it to index. So it basically looks inside all the installed packages and stuff. It gives you linting. So at the moment it still not sees it, so let me just wait for it to finish indexing. Now it sees it. The error is gone. So if you click on it, if you hold the control key and click on it, you can go inside the folder, inside the actual code of each one of these. Right? So if I run this, if I click on this and you press run, you can actually see the model training. Right, so I will play this demo so you can see what happens under the hood. So this is an actual training loop already happening. So I think it's just connecting the interpreter and stuff, and it's downloading the data. And let's give it some time. There you go. It's now training. So that's our sequential model. It's got 101,000 parameters. And it's now going over 10 training loops, training the model. And you can see the accuracy increasing every training loop. It started with 82%, and it's now 91%. And then we evaluated the accuracy at the end with our test images and test labels, and our loss is 0.3 between 1 and 0.3 is like a very small number, and then our accuracy is 88%. Yeah, so let's look at the code in detail. So let me make the screen bigger so you can see what's happening. So what I'm doing here is I have a bunch of class names in a list. So these class names, the order of the class names is basically represents the labels. So the best way to do this is if I put a line break here and then I open it with a debugger. You can do Command D on Mac. So put a breakpoint next to print, or maybe next to model fit. So just before we start training the AI model, and run the debugger so we could actually see inside the variables. And I will show you what each image looks like. So these are all our variables. You see down here, our test images. We have an array of how many images? is it 100, no, 10,000 images, test images, right? If I look at one of them, this is what the image looks like under the hood. What do you see? What is this? What does this look like to you? Any guesses? Let's look at another image. Let's look at the second image. This is the second image. Looks like a t-shirt to me. This is what the computer sees under the hood. You see, like, each this matrix of numbers represents the image. So if it's 1, you get a red. If it's 0, you get a blue. And anything in between, you get like a color between them. So this is a shoe. This is an image of a shoe. This is image of a image of a dress. And if we look at the, so this is the test images array. If we look at the test labels, if we look at the array, the first item is a 9, the second item is a 2, right? So let's look at our classes. So that's 0, 1, 2, 3, 4, 5, 5, 6, 7, 8, 9. So the first image is an ankle boot, which is exactly right. This is an ankle boot. And then the second image was a 2, right? So 2 is 0, 1, 2 was a pullover. This is a pullover. Right? So what we're doing is we're passing this array of numbers to the model. And we have about, how many? We've got an array, we've got about 10,000 images, each one 28 pixels in width, 28 pixels in height. These are test images. We've got 10,000 labels of numbers, which is like an array of numbers between 0 and 9. So that 0 and 9 represents these classes that I mentioned here. So this is a, if you want to convert those numbers into like actual names, these are what the names stand for in the correct order. So 0 represents t-shirts, 1s represents trousers, 2s represents pullovers, 3 represents dresses, 4 represents a coat. And then what the neural network does is that for each image, it will give you a probability score between 0 and 1, what it thinks it's looking at. So when I do a model.predict and I pass it an image, what I will get is an array of 10 numbers between 0 and 1. If it's a 1, it means that it's 100% sure that it's looking at an ankle boot. If it gives me an array of zeros, and if it gives me like an array of numbers. And we've got about 60,000 images of 28 by 28 that we use as a train image. So it's a matrix of 60,000 28 by. So think of this as a stack of numbers, like a massive cube of numbers with 60,000 labels that we pass to the image. So if you look at one of the train images, like let's look at the third image in here. If you look at the third image, this is what the third image looks like, which is, looks like a t-shirt. And then when you just use a matplotlib to plot them, this is what it looks like basically. The ankle book looks like that. I think this was a, what's this? I think this one is a t-shirt top, if I'm correct. That looks like a t-shirt top. Let me look at another train image. Let me look at this image. This image looks like a, looks like a normal t-shirt, so it looks like this. This looks like a pullover. So this is a pullover. right? And then if you want to basically look at the prediction, all you have to do is pass it one of the test images. So remember the first test image. What was the first test image? If you look at the first test image, it was an ankle booked, right? So if you pass this first test image to the model, let's see what we get. So let me stop the execution and let me put the let me print this. Let me put the execution here, and let's run the debugger again, and let's for the model to train up, and let's see the output afterwards. So while it's doing it, let me so that's the shoe, you're right. So Simona, it gives you a list of probabilities. So probability, think of probability as like someone telling you like, I think I'm looking at a cat. I'm not 100% sure. I'm like 60% sure it's a cat. It might be a dog as well. I'm like 20% sure it's a dog. It might be a car as well. I'm like 5% sure it's a car. It might be an ankle boot as well. I think I'm like 98% sure it's an ankle boot. That's how the model gives you predictions. Like for every class, it just basically thinks like what it might be, and it gives you a list of confidence percentages. And you can convert that to one number if you want to. You can convert it to one label and say like this is an ankle boot, like that. You can take the maximum. You can take the convert that list of probabilities to just one single class name. So let's run this line of code and see what happens. So if I run this line of code and I look at the output, I need to basically pass it in as a as the wrong shape. So you need to pass it as a list, basically. So if I go to model.predict, so if you just pass it as test images, you just pass it as a list, it will not work because of the size. So normally what you need to do is you need to pass it as a value, basically. mp.explode, for example. Need to import numpy. So one of the things that you will run to normally with what's it called? With Tensorflow is errors related to shape of matrices. And as you just saw here, I cannot just pass the first image as is to the model because it doesn't expect the image as it doesn't predict using it doesn't basically this test image, like if I just do test images, sorry, that's the test image, right? If you look at the shape of it, it's a 28 by 28 pixel image, but actually what the model is expecting is it's expecting a matrix of numbers that looks like this. A one-dimensional, a batch of 1 images, or you can have a batch of 10 images, and 28 by 28 pixel. So normally you will have problems with, like you need to pass in the same shape, like you need to pass the numbers in the same shape as you trained the model in. So we trained the model in shapes of 64 images of 28 by 28. So we will need to exactly expect a prediction similar as well. Either we pass it a batch of images to test, or we basically do something different, right? So I think there was a, if I remember correctly, was it expand or explode? Expand dimensions, I think. Expand dims. And if I pass the test image and I look at the shape, let me see what it gets. There you go. I need to expand the dimensions by 1. And then if I save this to a variable called image, and then now I do model.predict, I should be able to get the results, hopefully. They didn't like it, did it? Oh, I need to flatten it, yes. I forgot that this, so you need to flatten it basically before you pass it in. If I remember correctly, it was like the flatten test images, sorry. So that's the test images, and then if I flatten it and then look at the shape, that's the flattened image. I think I can pass this instead. So if I flatten and I do model.predict, then hopefully it works. Otherwise, I don't know. You know, these are like the problems that you will run into. It says input 0 of layer dense is incompatible with the layer. Expected access 1 of f input shape to have a value of 784, but received an input with shape none 1. I think another thing we could do is we could do it this way. We could just do model.predict and pass all the images, and then what it will return us is y. So test images are just basically, if I look at test images, they are 10,000 images, 28 by 28, and basically what you could do is, now that we have y, if I look at y, let me see what y is. So y is 10,000 images of a list of 10. So for each of those 10,000 images, we get an array of 10 numbers in it. That's the output of the model. So if I look at one of them, let's look at the first image. This is what you get, right? These are called logits. So they are the raw output of the model on them. What you normally do is you pass these numbers through a softmax function to convert, to normalize them between 0 and 1. Right? And I think from logits true, if you do this from logits true, I think it will basically allow you to perform the prediction. It's not that has it, it's the evaluate. So this is the output, and then basically you can normalize it to get the exact predictions between 0 and 1. That's step confidence interval. So you could look at the classes of that model. Any questions on this? So that's the prediction that was made on the first image. So if you remember, the first image was, what was the first test image? If you look at the debugger again, we look at the first test image. The first test image is an ankle boot, right? Yeah, so that's the first test image. That's an ankle boot. This is what we got for the ankle boot. If you look at the Python console, no wait, where is the debugger console? Yeah, this one, sorry. If you look at the debugger console, we got this array of numbers as the output of the neural network. And then the classes, the class names. The class names are this, right? So basically for each class name, you get these, you map these numbers to each class name. And before you do that, you basically use the softmax function to convert this array of number to an array of number between 0 and 1. And you can see already, just by looking at this, that ankle boot has the biggest number. You see this is an integer plus integer. The rest are like negative integers. And just by looking at this, you know that this prediction is very strong on the ankle boot and not very strong on the rest. That's the output that you get. From this. Any questions? So that's the definition for a softmax function. So if I just take this definition and I put it here, right? And I just do softmax, and I pass it the prediction. You get these numbers. And this logic that you see here, let me close this. It's really good for beginners to work with TensorFlow, but the problem with TensorFlow is that it's very hard to debug just because most of the logic is taken away from you. So the whole, like, what you do is just to do model.fit. But what you need to do instead, what you want to do is, some people prefer PyTorch just because with PyTorch, if I just look at the code down here, most of the logic is the same. Like, you need to construct your network model and you define your loss function, learning rate, and optimizer, just like that. But the thing is, when you go to the training loop, you actually have to write your training loop yourself. And this actually shows how the model learns. So if I run this on debug mode, and I get to dispatch, I would be able to show you how actually under the hood, when TensorFlow trains a neural network, I can actually show you in PyTorch how does that look like in a more Pythonic way. All right. So some people, like researchers, normally prefer PyTorch compared to TensorFlow, just because with PyTorch it's more Pythonic. Like you have, you can see how numbers are changing under the hood. Everything is not so abstracted away from you. And you have more control over your training loops and your testing loops, and the cycles that you run the code on. in order to train your model. So it's downloading the data at the moment. All right, now we're here. What we've done here is we have about 60,000 images of MNIST using the data loader. The first batch of data is basically 64 images of a single color channel, 28 by 28 pixels. We basically load them onto the CPU. We load each tensor into the CPU. If your device is set to GPU, it loads that tensor into the GPU. Model.x basically means model.predict. It passes that through the model.predict, so you get this prediction tensor. So you get an array of 10 numbers, and this prediction tensor is basically, if I look at the data itself, like go down the rabbit hole, isn't it? If you look at the data itself, you see like this array of numbers between 0 and 1. That represents your probabilities, like what the confidence rate is for each value. We calculate the loss. So we basically compare the prediction versus the actual label, and we calculate the loss. So the loss is 2.3. What we then do is we go and do a backprop, which basically means we're going to go back and see how much we need to change the knobs and dials. And this is what the optimizer does. It basically sets how much it needs to change. It calculates that. It then loss.backward goes back to the knobs and dials and change the knobs and dials. And then optimizer does steps, basically applies those knobs and dials changes. And it goes to the next step in the iteration loop. And basically it keeps doing that in each batch. It keeps looping in each batch, and it calculates per image. And we're still in the same, we're still in the first epoch. So if I basically take this off and I look at the code, it's doing this quite a lot. So if I take this off and I let it run, we're still in the first epoch. We went through all the images. We finished that epoch. We're not going through the second epoch, and we're going through all the images again in the second training loop. We went through all the images. In the third training loop, we will go through all the images again, and we calculate the loss. We go back, change the knobs and dials. We take the next batch of images in. We train again. We go back, test the next batch of images again, and we do this repeatedly until our neural network is trained up. And if you look at the average loss, it was 3.4 in the first epoch, 3.1 in the second epoch. The accuracy was 53. Now it's 60. Now it's 60.2. 60.2.4, all the way to the rest. And it's actually doing much worse than the TensorFlow one. I think because of the neural network architecture we have defined. This neural network architecture is just basically using ReLU activation functions, and it's just a bunch of linears. But I think with this one, if you look at this one, we are using a flatten, a dense layer, and another dense layer. But I think the optimizer we're using is Adam with TensorFlow. The optimizer we're using here is it's a much simpler optimizer. I think this one is a stochastic gradient descent. Oh, it's a cross entropy loss we're using with stochastic gradient descent as the optimizer. So SGD is a very simple optimizer. Adam is a very more complicated optimizer than SGD. And in here we're using sparse categorical cross entropy as the loss function, but in here we're using cross entropy as a loss function. So this is more suitable for the data set we have. that's why the PyTorch model is not performing as well compared to the other one. It's actually now at 68% at the 10th training loop. So with that, we'll let this train, see how much we get. I think, so if you play with the neural network architecture, you can actually go past, like you can even, with this data set, because this is a simple data set, you can go all the way to 100% if you play with this. So see if you can actually increase the accuracy to 100%. It's actually 70%. Normally you increase the accuracy by basically adding, by increasing the number of epochs, or by playing with the hyperparameters. So hyperparameters is basically what optimizer you use, what is the batch size that you play with. So batch size is in each batch how big the batch should be. So here the batch size is 60. I think I haven't passed the batch size here, but the number of epochs is a hyperparameter. The batch size is a hyperparameter. What loss function you use, what optimizer you use, what learning rate you use. These are all like different hyperparameters that you can use to figure out, to basically experiment with improving the accuracy of your model. And these are basically things that you play with. So sometimes what people do is they, oh, here, look at this. It says done, predicted ankle boot, actual ankle boot. Nice, well done. So basically with model training, normally what people do is they train multiple AI models at the same time with different hyperparameters. They normally do like a grid search in hyperparameters. Like they change the learning rate, the optimizer they use, the loss function they use, and then see which one works the best. All right. So with that, that concludes the workshop. There is some more content, but I think we're going to leave them for the next workshop, which is around how should you prepare your data and what are the things you need to look at. Plus, maybe we look at some convolutional neural networks as well and how they work. Any last questions? So just to remind you, there is the let me go back to slides. So this is part of a series, these workshops that we'll be organizing more of them, covering both TensorFlow, PyTorch, and neural network programming. The content will be placed on the platform once it's launched. At the moment, the platform is located at buildyourai.com, so it's still not fully functional. But if you would be interested to be more involved with the content that we will place on the platform and helping me with building the platform itself, yeah, let me know, and I can get you more involved with the actual with the extra content we're gonna put up there that we won't probably be covering in the BML workshops. So this will not just cover the data stuff. It will also cover databases, computer vision, data engineering, front end and back end as well. So how you actually build the whole app back to back. And you can learn more about it on the website as well. So I'm just gonna stop sharing my screen and just see if anyone has any final questions, and I will be happy to answer them. So how did you guys find it? Was it good? Was it too fast, too detailed? Well, how was the pace? Good. Yeah. I think I missed one question from Ibrahim. Um, he was asking, why do we need all the layers? How do we decide how many we need? Um, that's a good question. So that comes back to when I said it could be an art or science. So the more layers you add, the more knobs and dials you add. The more knobs and dials you have on training, the more patterns you can match, basically. So if you feel like your data has a lot of patterns in it, add more layers. If you add too many layers, you may overfit as well. So you may want to, so there's a trade-off. If you add too many layers, you may overfit your training data. So on your actual data, your model may not perform well. And also, the bigger the model, the more computational power you need to process data through it. So if you have a massive deep neural network, that's a very heavy neural network, and it takes ages to take data through it. So it's better to start with like simple neural networks, and if the accuracy is not good, keep making it more complicated, add like more layers, add more different types of layers and stuff like that. Play around with activation functions to see which one works better. So it's more like a experimentation mostly. Any more questions? So I didn't get that question, Ash. Yeah. I suggest, it's a journey. So it starts with learning the basics, which is programming, and then afterwards gradually going into simple problems around programming neural networks, and then from there going on. So like, because um, it's these are hard concepts. Like, you can't expect yourself to learn it in 2 hours in a workshop. This was just like to show you what are the things out there, and like give you most of the concepts. However, um, the easiest way is to go through structured courses. Like that link I posted on TensorFlow, that's a good one because you can play around with the code, and you could run cells and see how it interacts, and it gives you some concepts as well. No worries. And no worries, watch it. I hope you enjoyed it. So Sophie, Alex, I'm glad it actually was really useful for you. I'm gonna run more of these workshops. So I think next one, I'm gonna do one on NLP. So if you wanna learn how to actually work with natural language processing with text, other than just images, and then one on images as well. Um, there are also a couple I'm gonna do on machine learning, and also there is also one I'm gonna do on actually connecting bunch of cloud services together. So I have a workshop where you actually predict whether you've seen polar bears in North Pole or not. So imagine you have some IoT sensors in North Pole, and you've installed some cameras, and you're running an AI model to see if you've spotted polar bears in these cameras, and you have to build the whole thing in Azure. Like, you instantiate a database, you put Azure functions in place, you put the streaming analytics in place to do stuff, IoT hubs, like all of that. So it's very interesting. I've been running those workshops a couple in past, and people really liked it. So I will keep an eye for new events. And also for the buildyourai.com website, the platform I'm building, I'm writing the code still. There's a lot to write of code. There's a lot of code to write, but the forms are not working on it yet. But once I put the forms in and they work properly, I will let you know. You can sign up for an account, and I will put the content of this workshop and previous and future workshops on the platform, plus the content we're going to create, which includes both front end, back end, and all the data science. And it's going to be project based, so you will basically build a whole app from scratch. We will start with an empty text file, and you're going to have a proper working app by the end that has AI in it. So you would be able to build your own AI apps as well after that course. Yeah. Yeah, it will start from the basics and go from there. I think it would worth having some maybe Python courses as well. I think I may do some Python courses, I guess, before we go into before we get into advanced concepts. But there's a lot to learn. Like, there's so many books, so don't worry. We will challenge that together. All right. Yeah. Yeah. Install NumPy, PyTorch, and yeah. No worries. All you need to all you need to do is run this command in the terminal in your environment, and it should work. The command I posted. Yeah. Oh, that's interesting. Yeah. Interesting. Yeah, it might be an issue with either internet or the environment, but it shouldn't take that long because you just saw it installed on mine quite fast. Maybe create a new environment and try in that. Maybe there is some dependency issues in the existing environment you have. Like, yeah, it's like a maximum a minute or two. Yeah, like if it doesn't work, yeah, I mean that's why I taught you. I wanted you to learn to set up your own local environments. If it doesn't work, you can use a Google Colab as well, or online Jupyter Notebook websites, like an online website where you can run your own code. The Google Colab has like Tensorflow installed, so you can work on it. Yeah, yeah, I think. Yeah, one of our friends said, I think what just says, yeah, he had a problem with it as well, and he had to check if you have Python 64 bits installed. I think it's normally the issue with Windows. Because it's not pre-installed similar. It doesn't work similar to a Linux system. You probably need to use Anaconda or package managers like that to make sure that your environment is set up correctly. So I would use the Anaconda manager, which is this Anaconda Navigator. Use Anaconda Navigator to install your environments. Yeah. But that's a good note. Yeah, I think in future ones I will use Anaconda to make it easier for everyone to follow. All right. Thank you very much, everyone. I hope you have a good evening.